Geek Wisdom.
Disclaimer: the views and opinions expressed in this article are those of the authors and do not necessarily reflect the opinions of my employer. Examples of analysis and code used within this presentation are only examples. They should not be utilized in the real-world products, as they should be considered as based on limit and possibly dated open source information. Assumptions made within this presentation are not reflective of the position of any private or government entity to which the author is presently employed.
A while back, I had a problem. You may have seen this problem before. My toilet was clogged. Now, I don't consider myself a very handy guy, but I went to get my trusty plunger to try to unclog this porcelain masterpiece before it got any worse. Try as I might, I could not get the thing declogged. By the way, did you know there's two kinds of plungers? One for a sink and one for a toilet, and they're not the same thing? After trying for a while and not being able to get any further, I went out and got one of these snakes, which kind of goes down into your toilet and tries to declog it that way. 30 minutes later, still couldn't get the thing declogged. Okay, so yes, maybe at this point I should call a plumber, right? I mean, that would be the smart thing to do at this point. But of course not. I scrounged around looking for some tools out of my trusty toolbox, and I got a screwdriver and I got a monkey wrench, and I basically pulled the entire toilet apart. Interesting things about toilets. Did you know inside, underneath, there's this thing called a wax ring, and the wax ring sort of seals the toilet like a gasket to your connector. I think it's called the flange, and keeps the water from leaking all over your floor. Another interesting thing about this is when you remove the toilet, the wax ring basically becomes removed and you have to buy a new one. So out I go to the hardware store again. Now, wait a minute. Isn't this a session on component-based architecture? Where am I possibly going with this, you might ask? Shh! Come here. Come closer. Right up to the monitor. Closer. I know you're not really coming closer. I can tell. Wayne, now come closer. Closer. Are you listening? I'm about to reveal to you a very important secret. So don't tell anyone. Shh. Are you ready? Here we go. There is nothing new in computer science. In fact, there is nothing new in information technology. Nothing. I call this Brad's special analogy hypothesis. Everything that can be discovered or known or invented in computer science or in information technology has already been discovered, has already been invented, has already been known. Now you say to yourself, how can this possibly be? We know technology advances so fast, people can hardly keep up with all the new terms, with all the new things, the way that things are working. But all we're really doing is coming up with new ways to solve the same old things. And even those new ways aren't really new. They're based on initial concepts, initial ideas that were expanded on, and we changed some of the terminology around to make it sound a little bit different, give them a fancy name for the same thing. Now, I first came up with this theory back when I first learned my second programming language. So my first programming language was in BASIC, Beginner's All-Purpose Symbolic Instruction Code. And when I first learned BASIC as a young child, I learned concepts such as variables and loops and if statements. And I learned the famous goto statement and subroutines and functions and how this all works and how this all comes together. When I learned my second language, which was C, it didn't take me long to realize all these same things are there. They look a little bit different. The way you write an if statement in C isn't the same as you write an if statement in BASIC, but it's still an if statement. Loops, whether they be for loops or a do while loop, work the same way. Just the way that you type it is different. Variables, same thing, work the same way. If you want to learn another language like Java or like .NET, you're just taking those same concepts that you already know. Even within languages, we say we have functional programming languages or procedural programming languages and object-oriented programming languages. But they all still have the same basic concepts. They still have the same basic ideas. And when they build and they compile, they get broken down into the same machine code that has to execute on the computer to do those instructions. So there's nothing new. It's just a different way of doing the same old thing. And this expands beyond just the idea of programming. It expands to a lot of computer science concepts, a lot of ideas around the internet and around communication, whether we be reading or writing a file versus reading or writing an internet socket versus reading or writing over a communications port. It's the same idea. Different terminology. We refer to in communications, we might say that it's the data terminal device. But in sockets, we may call it a client or a server. Different words, the same concept. Think about a television. You probably have one of the latest, greatest high definition or 4K televisions. And it doesn't have a picture tube anymore, right? It uses LCD or LED technology. But the concept of displaying stuff on the television hasn't changed. We've improved the way that it looks, but we didn't create anything new. So this leads to what I call my general analogy hypothesis. We can say for any discipline X, and that could be computer science, it could be engineering, it could be art, it could be literature, it could be history, everything that can be discovered, could be physics, everything that can be discovered about that thing has already been discovered, has already been known. In fact, in photography, they have a special word, and I'm not going to pronounce this correctly, I'm sure, Vemodalen. And it's defined as the fear that every photograph has already been taken. So if you're into photography, you may have just captured an amazing photograph of a sunset or an amazing photograph of a lightning bolt or something in nature that you think, wow, nobody's ever captured this in quite that way. And then you do the research after you've developed the photograph and you realize that there's hundreds of photographs just like the one that you did. They're already been known. They've already been taken. One time I was out on the step and I seen a spider that I had never seen before. I thought, that's a cool spider. And I took a picture of it to see, what kind of spider was that, only to realize it basically was just a common household spider. I just never seen that kind of spider before. And I thought I took this really cool photograph and I posted to the internet and quickly got a response, oh yeah, that's this spider. And it's already been classified. It's already been known. In fact, this goes so deep that even my hypothesis has already been invented. So there's a guy in 1899, he was a commissioner of the U.S. Patent Office. His name is Charles Dewell. And he's been attributed to the expression, everything that can be invented has been invented. And there's some debate around whether or not that was his statement, but that was the idea. In physics, in fact, Max Planck, also around the 1800s, was sort of debating whether or not somebody should even go into the field of physics, because at the time he figured everything that can be known about physics has already been known. There's nothing new to learn. There's nothing new to advance upon. So we do learn, we do expand on our existing thoughts, we do change our wording, but we basically just reinvent something else. And we say that thing is the same as this thing. So you can learn by analogy, and you can fastly learn new things by taking what you already know and just expanding upon what that is, what it is from a general sense and what it is from a specific sense. Very similar to Einstein's theory of relativity. In fact, even before this 1800s, there's even an older quote from the Bible. What has been will be again. What has been done will be done again. There is nothing new under the sun. So what exactly is component-based architecture? Well, it all starts millions of years ago. Animals started to use tools. Some of the early reports show different varieties of chimpanzees and gorillas would use sticks to get at ants at trees, or might make a simple rock in order to bash something down. The Stone Age is when the first human stone tools are dated to have been used, about 2.5 million years ago. And I think we can all agree that in our modern age, computers are our most advanced tool that we use today. Those computers are built inside things called integrated circuits, a specific piece of hardware that was designed for a specific function. Then around 1968, a named Douglas McIlroy, he was at a conference in NATO, and he did this conference called Mass-Produced Software Components. So he basically took this idea of tools and things that we use in everyday life and said, couldn't software work the same way? Software that's designed to perform specific functions and could be reused, prefabricated as needed. So the definition is a software component is a unit of composition with contractually specified interfaces and explicit context dependencies. A software component can be deployed independently and is subject to composition by third parties. Isn't that a great sentence? One thing we never fail to seem to do in the English language is come up with very complex terminology to make ourselves sound smarter. And this is a good example. So a software component is just like a tool. We would use it like a hammer or a drill. It has a certain feature and a certain function and a certain way of communicating with it, which we call the interface. So let's say, for example, we've been asked to design a travel management system. So something that would help people prepare for their trips, let's say to Las Vegas. And on planning that travel management system, they need to consider the different components that would be involved. So they'll need a way to do their hotel reservations. So we'll have a component for hotel reservations. Or they'll need to rent a car so they can drive around to the various casinos for their fun time gambling. And of course, you'll need some sort of flight reservation unless you live really close to Las Vegas. If you live in a faraway area or a faraway country, like I'm in Fredericton, New Brunswick, Canada, I'm going to need to book a flight to be able to get to Las Vegas. So these are some different components. One component that you don't see here is a menu. Somehow I'm going to have to navigate a menu of this system to figure out which component I want to go to that's going to take in my data from my reservation and store it somehow. So that'll be a component as well. Now, we can further break down components into different subcomponents. Think about layering. So that hotel reservation component is going to have some sort of feature that's going to take in those details. When am I going to check in? What date am I going to check out? There are going to be other details, obviously, what my name is, how many rooms I'm going to need, whether or not I need smoking or non-smoking, things such as that. But it's also going to need to verify that the hotel is available. During that time, can I stay in that hotel? Maybe they're all booked up for some huge conference for Toastmasters, for example. So they don't have any availability of rooms. And of course, they're going to need to somehow take my payment. So whether that be my credit card or cash or Interact Debit, they're going to need some system that's going to process my payment. So they might be subcomponents of the hotel reservation component. So we have a hotel reservation component. Maybe it comes from a common component of reservations. So all of the concepts around reservations don't have to be specific to hotels, right? But there's going to be some way of intaking those details of the reservation. It could be for a hotel, could be for a car, could be for a flight, but the same sort of concept applies. You're going to have to verify availability. So for today's learning presentation, our examples are going to be written in C#. C# is a subcomponent of the .NET programming language. So it's one of the languages you can use for .NET, and we're going to use C#. We're going to use the built-in C# compiler that's included in pretty much every variant of the Windows operating system, at least since Windows XP. We're not going to be using any fancy development tools or fancy integrated development environments, but if you want to get something like Visual Studio Express to try these out, you're certainly welcome to. Or you could get Sharp Develop, which is a nice little IDE. But we're going to be doing most of this on the command line using the C# compiler. And if you have a Windows system, then I guarantee you .NET is installed, and I guarantee you have a .NET compiler. These all just come built into Windows, no additional cost whatsoever to you. So let me give you a quick example. I'm going to open up my command prompt here, and I'm going to look for a directory called Microsoft.net. Okay, so that's where all of the framework is. And if you look in that directory, you'll see there's a folder called Framework. And for 64-bit, there's a Framework 64, but let's not worry about that right now. Framework, and then in that Framework folder, you'll see the different versions on your system. Each version is a different directory. So I'm going to go into the version 4.0.3 folder, and that's where the version 4 or 4.5 or 4.5.2, it all uses the same folder for some reason, but that's where it's stored. And in there, the actual C compiler is called CSC. So that's the C# compiler for the .NET Framework built into your Windows system. So to be able to use it, I'm going to simply set up a path. I'm going to add to my existing path that folder so that it knows percent path C Windows. That same folder, Framework, version 4. So now when I type CSC, it will always find where that is. So let's move to the G drive. Training components. And we'll look at listing1.cs. So that's our first C# file. And if you want to see what it looks like, I can open that in Notepad. Okay, so this is a very simple C# program that I created. Now, if you're not familiar with C#, but you are familiar with .NET or programming, you can pause the video now, do a few Google searches on C# tutorial. That'll get you up to speed, and I'll just wait for you, and when you're ready, you can come back and continue this video. Okay, so through the miracle of modern technology, you've gone out and you've learned C#. Okay, so let's look at our first example. It's a very simple program. It has one function called main, which is going to do the main running when you run the program. It basically assumes there's going to be a file called menu.txt. And if that file exists, then it's going to read all the lines of that file, and it's going to write the contents of that file out to the console. So if we take a quick look, we'll also see that I have a file called menu.txt. And in that, I have a very simple menu for our fake travel management system that we're working on. I can simply compile the program by calling the compiler CSC, and then the name of the file, listing1.cs. And when I hit enter, if I see I get no errors, it would have created a file called listing1.exe. I can run listing1.exe, and it will show me the contents of the file. Now I could go in and I could change the contents of menu.txt, and I could add, say, please enter choice. And now when I run listing1 again, I see please enter choice. Now in our example in listing1, everything is done inside this main loop. Now we know from our various programming courses that putting everything inside the main function is not very easy to maintain. In fact, it creates what we call spaghetti code. And the reason we call it spaghetti code is when everything's in the main function, we can't figure out when one piece of code starts and where another piece of code ends, or where one part of functionality starts or where the other functionality takes over. It just kind of loops around like all these different spaghetti loops. So we get around that by creating individual areas of our program into their own functions. So as a simple example of that, let's look at listing 2. So in listing 2, instead of having everything happen in the main function, we simply created a little sub part called show menu that takes in a file name, shows the contents of that file name, and our main function runs that menu.txt by calling that show menu. So it's a little easier to maintain, it's a little easier to read. Still not perfect, but it gives us that example. So now I can compile listing2.cs. We can see that it works the exact same way, but I've sort of separated that layer so that it's not all running in the main function. Made it a little bit easier to maintain, but we can get even better than that. Now, as humans, we just love to classify things. I'm not sure why that is, but we even have a name for it. The science of classifying things is called taxonomy, not to be confused with taxidermy, which has to do with the stuffing of animals. We classify things that are related into groups in our programs by generally, for example in C#, making them into their own classes. So we can see an example of that in listing 3. In listing 3, I no longer see that menu system show menu. I put it into its own class. So the menu component, is its own class separate of the main function. So now, again, I'm separating things even further apart. I'm saying all of my common menu type routines will be stored in a menu component, and that menu component will work with that main program together to generate the menu. So now I have two separate files, one that I'm going to keep all my code for menu components in, another one that I'm going to have for my main function. And I can continue to elaborate on this idea and have different classes for different areas. I might have one for hotel reservations, a CS file for that. And I might have one for car reservations. And I might have another one for flight reservations. All these different components coming together. Now, when I want to use them together, I'm going to compile them together. So I'm going to compile the listing3.cs and I'm going to compile the menu component.cs together so that the compiler can link all of these things in what we call static linking and create a new listing 3 that still does the exact same thing. But what I've done is I've statically linked the two programs together. In fact, I created a file that's a little bit bigger because it took those two parts together, listing2.cs, and it merged them into the same file. So that's why we have a bigger file now. Now, when we link those two components together, as I use the word statically, meaning both the main program and the component are stuck together, we can also do something what's called linking dynamically. So in this case, we'll actually have two binary programs, two executable programs. One will be for the component. It's going to be stored in what's called a dynamic link library. And then the main program, which will be stored in its exe. So to do that, I'm going to first compile the component, menu component.cs. But I'm going to tell the compiler that it's going to be a library. Now, if you're familiar with Visual Studio IDE, this is the same as creating a new solution, and when you create your new solution, you say your target type is going to be a library. And I'm going to say it's going to create a DLL, so I'm going to say its output is going to be called menu component.dll. So that's going to compile just the menu component into a file called menu component.dll. By itself, it has no main function, so it can't execute on its own, but it'll sort of create that class within that DLL file. So you can see now I have a menu component DLL. The next thing I'm going to do is I'm going to compile the main routine. So that listing 3 again, this time I'm not going to put menu component.cs. However, because it has a DLL that it needs to know too, I have to use this R switch, meaning include this DLL. So it's not going to compile anything for the menu component. It's going to compile listing 3, but in order to find its reference to the menu component, it has to know where that menu component DLL file is. So these are now going to become linked dynamically. So we can see now listing3.exe is about that size. Menu component.dll is about that size. So it's two files, one for the DLL, one for the listing. If I run listing3.exe, still does the exact same thing, but now we're linking dynamically. So why would you do that? Why would you want to link dynamically versus linking statically? Well, it's kind of interesting. Now, from a code management perspective, I can manage the component completely separate as long as I never change what we call the interface. I can manage the component completely separate of the executable. So what do I mean when we say as long as I never change the interface? So an interface is a boundary that connects the two programs together. So it's what connects the main program to the menu component. It defines the necessary inputs and outputs that those communications have to travel upon. So let me show you what I mean. I have a main program, I have a menu system, and I have a method in my menu system called showMenu. So showMenu is my interface, and it takes in an input file name, a path to a file name, and it outputs a string, which is the contents of that file. So as long as I never change the inputs and the output, it always will take in a string and nothing more and nothing less, and it will always return a string, which is the contents of that file name, nothing more and nothing less. I can compile it, the menu system, without actually needing to recompile the main program. Let me show you what I mean. I created a new one here called menu component version 2. So I've expanded on the original idea of the menu system. I still have the show menu method. It still takes in the same input, and it still outputs the contents of the file just like before, but I've changed it a little. I said, well, let's make the color green, and then when we're done, let's make sure we switch the color back to whatever color it was originally. I also added a method called doHotelReservation, which doesn't do anything right now, but just to show you that I can extend what the menu component can do. Just sort of gathers information about the hotel reservation. I'm going to recompile the menu component. So let's compile just the menu component as a new DLL. So CSC, target library, just as before, out as menu component.dll. So it's going to overwrite that existing menu component, and I'm going to compile menu component version 2, which creates that green file, that green output. So now we have a new menu component.dll. Now I'm going to run listing 3. Note, I didn't recompile the listing 3 main program at all. It's the same executable that it was before. It's now referencing a dynamic DLL, and I changed that DLL, but I didn't touch the interface. So what happens is when I run listing 3, now I see that I've changed the color and it's outputted, that common green screen format that's been used, in 1986. So let's review. When we link to a component statically, the main program and component are stuck together. If I change one, I need to compile both. If I link dynamically, the component in its own file, a DLL, and the main program is also in its own file. I can change the DLL, and as long as I don't change the interface, I don't have to change the EXE. Similarly, multiple EXEs can use the same DLL. I could create another main function calling that same DLL to show a different menu if I want it. When we link to a component dynamically, we can change just the component. We only need to recompile the main program if we decide to change the interface. Okay, so does this sound a little familiar to you? Well, it should. Any high-level programming language you've ever used uses components already. Consider the very simple Hello World application that calls console.writeLine in order to print the word Hello World. That console is simply a component that has a method writeLine, or an object in C#, and that's stored in a dynamic link library. You can even do a Google search for the console.writeLine method, and you will see in the .NET framework that it comes from the namespace system and the assembly mscorelib, which is just a DLL, mscorelib DLL, that automatically gets linked to your project when you build it. And if you've ever done anything in Visual Studio and you've had to add a reference to a DLL, that's what you're doing. You make that connection with that library. Now those DLLs are always included as part of the .NET framework, but it's the exact same thing. It's just a component that you're calling in order to perform a function. And that's basically all it is. So let's review. Components are like tools, just like the tool of the plunger that you use to get the water out of your toilet. But we organize them together in sort of a system of related functionality. So in the example that I gave here, you could have a menu system or all reservations, or you could have a system.io. Components can be linked either statically or dynamically. So when we link statically, the actual code is linked to the executable, so they become one big executable containing all of the information. And when they're linked dynamically, they stand apart. So when they stand apart, you can recompile the information in the DLL, and as long as you don't change the interface, they can both continue to communicate without having to recompile the whole program. So let's come back to the definition that I said earlier. A software component is a unit of composition with contractually specified interfaces and explicit context dependency. A software component can be deployed independently and is subject to being to composition by third parties. So it's basically a piece of work that we said it does this specific piece of task. It has a certain interface, so you have to communicate with it with a certain specified inputs and outputs. And it can be deployed independently. That DLL can be reused by other applications. So in my example, if I gave a menu system, I could reuse that menu system in a lot of different applications once I have designed it. So that's what makes up a software component. Now, we looked at how to build components, and we looked at examples of how to link components together and the idea of linking statically and dynamically. But we know that just because we know how to do it doesn't mean that we're going to do something well. So what are the qualities that we need to make sure that we give to our components to make sure that they're good components? How do we use this new power of building components to make the world a better place? So we're going to talk a little bit about architecture. And if you want to learn more, you can watch the video, Introduction to TOGAF, that will give you some more idea of architecture principles. But the main thing to remember here, we have a quote, "Those who cannot remember the past are doomed to repeat it." And that has been credited to many different authors. The one that I choose to be the person who said it, George Santayana, Volume 1, Reason and Common Sense. So we create principles to lay a foundation for things that we're going to build upon. And principles are things that people have learned about from years of experience of making mistakes, years of experience of trying things and figuring out what works and doesn't work, and then laying the foundation of those principles to follow so that we don't have to repeat the same mistakes twice. So we're going to talk about the principles that make up a good component. So as mentioned previously, tools have been around for millions of years. Software components, we could say since maybe the late 60s. And we've had a lot of time to make mistakes. So we've learned for those, and these are the principles specific to software components, but the idea is universal. The first thing we need to understand is, how are we going to organize these components? So we built a system of components. How are we going to keep them structured? How are we going to keep them everybody on the same page? So we need to group them into some sort of logical order. Take a minute and think about your kitchen drawer. And you open it up, and your utensils, you have a spot for your forks and a spot for your knives and a spot for your spoons, and everything is laid in that spot. So when you want it, you know exactly where to go to get it. And having a logical order that everybody understands means everybody in your family knows where to go for a spoon. Not everybody in my family may know where to go to get the yeast or where to go to get the soup, but we at least all know where we need to go to get the spoon. Now there's two common approaches to how we organize things. One is called top-down, and the other is called bottom-up. Now, I have a personal bias towards bottom-up. I prefer bottom-up, but I'm going to try to be very unbiased in my description of both approaches. But just to be fair, and so that everybody out there in La La Land is listening, I'm more of a fan of bottom-up. So what does it mean when we say top-down design? So in top-down design, our emphasis is on organizing first. So if you think about that junk drawer in your kitchen, Top down is about the idea saying, okay, I need a spot to put my spoons and to put my knives and to put my forks. I need a drawer that is going to be for my utensils, and I need a cupboard that is going to be specifically for my pots. And I'm going to need another cupboard where I'm going to store my baking supplies. So you're going to start by figuring out how you're going to categorize everything first. You're going to apply a structure and you're going to put it all in place before anything else. If you were to think about this in terms of folders, if you were to create folders and build a structure for how everybody in your organization is going to organize all their files, maybe you'll have a folder for your marketing, and maybe you'll have a different folder for your sales, and maybe you'll have a different folder for your specifications, and a different folder for your policies. And you work that all out in advance, and then you explain it to your organization. So one of the advantages of top-down design is the ability to do early estimation. So if you're able to break down everything into the different components that they're going to be and how those components are going to be organized, and you get that all done in advance, you can then say, well, it's going to take me this amount of work to work out this part, and this amount of work to work out this part, and this amount of work to work out this part. And that'll allow you to count the different things that you have and how long each thing will take, and then put them together to get a good sense of how long the entire estimate of work will take. It's also very useful when you don't already have something started, when it's the very first thing you're putting down, your very first pen to paper, and you're trying to figure out that initial organization, and you don't have some other mess or historical information to deal with. Top-down design can be really useful. It's also good if you're bringing in new people into your team, or you need to have a communication with your team and say, okay, guys, this is how we're going to do everything. This is how everything's going to be laid out. So you have an existing organization system already in place. Some of the sort of disadvantages of top-down design, we wouldn't say that things grow organically. Because everything's all been pre-planned and pre-worked out, there isn't really any evolution. There isn't really any built-in team improvement. It doesn't mean things can't improve with the top-down design, but it's very much a command and control kind of structure, and it's kind of takes people away from feeling like they can contribute because everything's already been designed for them. Also, it may focus less on the generic and reusable and the more specific need it now. So what I mean for that is you already have a problem you're trying to solve. You're already working on a very specific problem with a very specific domain, a very specific scope. So you may tend to be focused just on that scope and designing a solution that solves that problem, and not as much focus on, okay, how can I reuse this particular component in a bigger picture? So let's compare and contrast that with a bottom-up design. So in a bottom-up design, you're not really focused on how the whole thing works in one big piece, of having it all laid out and all organized in advance. It's, well, let's just see if I can get something to work. It doesn't have to be perfect. You're playing around, you're experimenting. How do I get a light bulb? Let's try this type of filament and let's see what happens. And then mistakes happen and you kind of just sort of evolve it as it comes together. It's sort of a more artistic nature rather than an organizational logic approach right away. Doesn't mean you're not going to apply logic. It just means you're moving forward and then trying to figure out how things organize as you go. So a bottom-up design is very useful if you've already started with, we'll say, inherited somebody else's mess. Maybe you already have a large amount of spaghetti code there, and you need to go through it and sift through it and figure out, well, I'm going to put this piece over here, and I'm going to put this piece over here. Its growth is organic. So over time, you're constantly improving upon it. You're constantly making it better. You're constantly asking yourself, okay, how can I take this and just tweak it to make it that little bit better? Generally, bottom-up design doesn't work on a strict schedule very well. So if you say, look, you need to have this piece of design finished by next week, it's not going to have that organic growth. It then becomes too structured. So it works best when you're doing pieces and piecemeal. When you have a little bit of time, you're going to work on it. When you have a little bit more time down the road, you'll pick it up and you'll work on it a little bit more. This particular presentation you're listening to is a good example of bottom-up design, because although there was some initial organization and some initial structure, it's very piecemeal. As I had the time to work on it, I put a little bit of it together. And then I sort of put all those components together into what looks like, hopefully, from your perspective, one large, well thought out organization. But it's actually been a bunch of little pieces that I just built on as I had time. So bottom up can look like top down depending on your perspective. So again, just like I said, where I put this presentation together in little piecemeal pieces, each one focusing on a different piece and then stringing them all together, when you look at it afterwards, it might seem like a top-down approach to you. It could seem like everything was all laid out and organized in advance. And of course, there was some laying out, but there was a lot of little piecemeal things that went into it. So it all depends on your perspective. If somebody's given you something that they've already completed, can you tell really whether it was top-down or bottom-up? If you weren't involved, it's not going to seem bottom-up from your perspective. It's going to seem top-down, even if the person that put it together really did it with a bottom-up approach. So let's talk about another principle that's sort of related to this, and it's the idea of cohesion. So if you're organizing your components and you're putting everything together, the best way to do it is to make sure that all of the things in that common arch have some sort of relationship, a very logical relationship, a relationship that's easy to identify and see. So let me think about an example. Suppose you had a component that was managing security, and you called your component the security manager component. Sounds like pretty obvious, right? One looking at that would expect that all the methods in that component would have to do with security. Now, it could be about managing permissions, or it could be about determining whether or not somebody has access to a particular page or a particular function. Perhaps it's about creating accounts or removing accounts. But you wouldn't expect it to contain unrelated functionality. So a routine that goes out and gets a person first and last name, because that would be under a separate type of organization. It wouldn't be as cohesive. So the better everything in your component structure is related to that structure. This holds very well with object-oriented programming, and not all languages are object-oriented. But for those that are, if you think about the idea of having an object called Security Manager, all of its methods that are public would be related to managing the security of something. So they're automatically related to that object. An object that manages user information, you would expect it to store information about your first name and your last name, age, telephone, contact type information. You wouldn't necessarily then also throw into that, details about your car or details about your relatives. You might have a relationship to them, but it's not all going to be stored within the same component. So another important point is reusability. So the whole point of using a component is that it's something that you want to be able to consume multiple times. You want to be able to save work moving forward. So I'm going to say, well, I'm going to use the same menu component for my new application as I used for the application that I did last week and the application that I used the week before. In fact, you could say that the component's usefulness is entirely dependent upon its capability for reuse. If you're just designing a one-off component to do one thing for one specific application, then why use it as a component at all? Why not just build it into your application? You're always thinking about reusability. That's when you start to think about components. How would this get consumed by other applications? How do I make the interface generic enough so that any application can call it and use it for its particular function and its particular need? Now, related, often when you hear terms of cohesion, you will hear something about high cohesion and low coupling. So coupling and cohesion go together. So where cohesion, we talked about how everything in that library, in that organizational structure of the component is related. Coupling refers to the amount of dependence components have with one another. So ideally, you want low coupling. In fact, the optimum coupling will work together with a common interface, but wouldn't even require the same programming language or even the same operating system. So let's think about an application where you want to get stock information. You want to know what the stock price is at IBM. So you might want to be able to call that component from within your Windows application, from within a web browser, or from within a Java application on a Linux system. So that component could be called from multiple different systems. It could be called from a stockbroker's computer, or it could be called from just Joe Blow who wants to log in and see how his prices are doing in his web banking account, and it needs to look up that stock information. So coupling, low coupling, means that getting rid of a component or changing a component doesn't require somebody else to change their component or how they talk to that component. That they don't even have to, as long as the interface is common, they don't even have to share the same language or the same operating system. Okay, number 3, and maybe this should have been number 1. One of the biggest things about components is what we call separation of concerns. The idea that whatever that component is doing, that's all it's supposed to do. And it allows the programmer to focus on, okay, I have a component that does X, and all I need to do is consume it. All I need to do is think about that get stock. I just need to say, give me the stock for IBM. I don't need to know how all the interrelated details work. Each component has a specific function, and it does that. Where concerns are separated, individual components can now be updated independently. So if the way of getting that stock changes, and instead of looking, I don't know, on the NASDAQ, I have to go look in the New York Stock Exchange, it shouldn't affect the way every other application that calls the component works. And as the developer, I don't have to know the details. So what does this mean? If we look at these first 3 ideas and we talk about how we're going to organize our components and how we're going to make sure that those components are reusable and how we're going to make sure that they are a separation of concerns, one thing and one thing well. What we're really talking about here is building things that are a black box, is building things that developers can use as tools without having to know the details of how each little part works. Now, obviously, if we're the one maintaining these, we need to know the details of how they work, but we need to keep those details separate from our mindset as a programmer of the people that are using them, the people that are consuming them. We don't want the people that are consuming them to need to understand all the details of how they work in order to be able to use them effectively. So a good analogy here is a car. If you know how to drive a car and you know how to start a car and you know how to keep the car on the road and you know how to stay out of accidents and you know how to apply the right speed limit and you understand what the turn signals do, you can understand all of those components to use a car without having to know anything about how the car works, without having to know anything about the internal combustion process or spark plugs or drive chains. None of that is necessary to know how to drive the car. If you're responsible for maintaining the car, if you're responsible for doing oil changes, if you're responsible for changing the tires, then yeah, you need to understand a little bit about the mechanics of the car, and depending about how strong the maintenance you're doing and what the problems you're trying to solve, the more you need to know about those details. But if you're just the consumer of the car, if you're just the user of the car, that's the idea of a component. A component should be something that as a developer you can use and you can get a lot of advantages of. You can take that reusability, you can apply it to a lot of different situations without needing to know the details. If you've implemented these topics properly, if you have a high sense of cohesion and a low amount of coupling, if you've applied a very logical structure to how you've organized your components, if you've made sure that each component is designed to do one thing and one thing well, then you can assure yourself that the people using those components are free to consume them without having to worry about those details themselves. Now, how do we do that? If we have a black box component and we want to make sure that all of these things are taken care of, what it really means is that we have a well-defined interface. So again, if we come back to the car analogy, I know that if I sit in a car, I should have a gas pedal. I should have a brake. They should be located in specific spots within the car. A steering wheel. If you've ever tried to drive a car, say, that was made in England, and things are on the opposite side, you may find that a little bit awkward because the interface for the car is different than what you're used to. So when you have a well-defined interface, people can call that interface, people can use that and feel comfortable with that without having to know all the nitty-gritty details. Changes to the functionality shouldn't change the interface. So if I put in a bigger engine that has more horsepower, I would still expect to find a steering wheel. I would still expect to find a gear shift. I would still expect to find a gas and a pedal, right? Those principles apply regardless of how I change the functionality of how the car works, regardless of whether or not I can get to 0 to 60 in 3 seconds or 0 to 60 in 10 seconds, regardless of whether or not I go through 50 miles a gallon, 100 miles a gallon, or 2 miles a gallon, the interface should still be the same. If you need to change the interface, you need to do it in a way that ensures that it's still backward compatible to everybody using it. So if I do add something to the interface and giving it new functionalities, then I still need to make sure that the old way still continues to work so that everybody doesn't have to rewrite their application to match with the new interface, unless they choose to. Our fifth principle is a little bit tricky to explain. It's called open for extension, but closed for modification. And this sort of ties with the idea that was just previously mentioned. If I have a component and I have a well-defined interface and I don't want to change that interface, but I want to give it new features, how do I modify it and ensure that it doesn't affect other people that are using the component? So basically we say once we have a good working component, once we've finalized it, once we've spec'd it out, once we have everybody agreeing on how all that spec works, once people have started building towards using that component, we're going to make it closed for modification. We're basically going to say we're not going to change the code in that component. And then you say, but what if we need new features? We're limited. We need to do other stuff. Well, a common concept that you know of from doing object-oriented programming is the idea of inheritance. If I have a component, say the Security Manager component, I can create a new component, Security Manager 2, that inherits all of the properties of Security Manager, but gives it new features. By doing this, everybody who uses the Security Manager component can be comfortable in knowing that using it will still always work always the way that it did. Nobody's ever changed any of the code in that component, but they can use the extension amount of the component to do other things in addition to everything that it already does. If new features are required, especially if there needs to be an interface change, then you can create a new class that defines how that interface change will be without touching the way the existing interface has always worked. So we call that open for extension, but closed for modification. So don't change the original source code if you can inherit the properties of it and extend upon them in a new class. Okay, so then now we've learned the basics about components and the basics of component-based architecture. What is a component really? You should understand that now. And what are the qualities that make high-quality components? We also learned the principles of designing a good component. We've looked at some example code of how we would build components, of how we would do dynamic and static linking. So in our next presentation, we're going to expand further on components. We're going to talk about two specific concepts known as inter-process communication, or IPC, and also RPC, remote procedure calls. Now, there's something very special I need to thank today. This presentation wouldn't have been possible without this particular thing, without this particular aspect that if it wasn't for it, it would have been so much more work. It would have been so much more labor. And what it is that I really need to thank is components. Today's presentation has been brought to you by components. If you were to look at the actual Movie Maker presentation, I had an existing intro component, which gives my little intro to my presentation, shows that sort of that cool little starting video. Then I have the disclaimer that plays for a few minutes that is added to all of the videos as I put them together. Then we sort of have the meat in the middle, and you might be fond of my hypothesis, my general hypothesis and my specific hypothesis, which I'm sure you've seen now throughout the different videos that I do, and then the little disclaimer that you'll see at the end, all put together by components that were reused for each of these different pieces of training. So let's look forward to our next exciting episode.